Hello everyone, I am Dr. Vandana Yadav, Assistant Professor, Department of Science, the Bhopal School of Social Sciences, and today we are going to discuss alkanes, one of the most fundamental topic of organic chemistry. We will go over the structural properties and conformational analysis of alkanes. So here we are going to start with alkanes. Alkenes are the hydrocarbons, that is, they contain only two elements, carbon and hydrogen. We often use term aliphatic hydrocarbon for alkanes because aliphatic word is derived from Greek word alipher, which means that they are derived from plant oil or animal fat. When we will study higher alkanes, we will observe that these alkanes resemble the properties of plant oil and animal fat. Therefore, we use the term aliphatic hydrocarbon for alkanes. Alkanes are also called saturated hydrocarbons because they only contain single bond in their structure. Now coming on to the basic class of organic chemistry, alkanes are having general formula of CnH2n plus 2. That means for each n number of carbons, there are 2n plus 2 number of hydrogen present. For example, considering carbon is equal to 1, that is the first member of this family is CH4, which is called methane. The structure of methane is 1 carbon bonded to 4 hydrogen, and each carbon is sp3 hybridized, and the angle is 109.5 degree. So this is the first element of this family, which is called methane. Moving on to, if I am having 2 carbon, then I am having C2H6, which is called ethane, then C3, H8, C4, H10 and so on. So as the number of carbon increase, the number of hydrogen also increase, and we get our list of alkanes. Now these all alkanes are similar in their properties. Why? Because they all are having sp3 hybridization and their bond angle is nearly the same, that is 109.5 degree. So therefore, all the alkanes starting from the lower ones to the higher ones all are having similar properties and they are showing similar chemical reactions. Before moving on to the structural property of alkane, let's see how we are going to represent the structure on paper. So we have 3 types of representation. First is the Lewis structure, second one is the condensed structure, and third one is the line angle structure. So on a piece of paper we have 3 representations. First one is Lewis structure, taking the example of 3 carbon, that is CH, 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 H, H and H. If we want, we can also show the electron forming the bond. This is called the Lewis structure of C3H8. Now coming on to the condensed structure, I have CH3, CH2, CH3, and the line structure is like this. Line structure means each vertex is showing the presence of carbon. We do not show hydrogen in this structure. We automatically assume that the number of hydrogen will be those satisfying the valency of carbon. So these are the 3 representation of a particular alkane. Very often we categorize carbon into primary, secondary, tertiary and quaternary. This is important to study the chemical reactivity of alkane. So let's see how we categorize carbon into primary, secondary, tertiary and quaternary. Let's begin with this example. Consider carbon at the corner. Each carbon is forming one bond with the other carbon. That means they are directly linked to one carbon. So, these carbon can be categorized as primary carbon. Now, coming on to secondary carbon, as the word secondary indicates that if any carbon is forming two bonds with the other carbon, then this carbon becomes the secondary carbon. Now, tertiary, as the name indicates, tertiary, that means if in any structure carbon is directly forming sigma bond with three other carbon, then this carbon is called tertiary carbon. Tertiary carbon. And quaternary means if it is forming four bonds with other carbon, then this carbon becomes your quaternary carbon. Later on you will see that primary, secondary, tertiary and quaternary carbon are important in alkanes because they decide the chemical reactivity of that particular alkane, and as well as they are responsible for the stability of different alkanes. So, we need to know the presence of primary, secondary, tertiary and quaternary in a particular alkane. Now, we are going to study the nomenclature of alkanes. As you have already observed that I was naming the first compound as methane. So, all the alkanes are using suffix "ane". So, you can use "ane" whenever you are naming any alkane with the prefix as meth, eth, prop, but, which is depending on the number of carbon present in the alkane. So, nomenclature is basically a detailed topic which is judged by IUPAC, International Union of Pure and Applied Chemistry. So, this we can later on study in detail. Now, coming on to structural properties. So, structural formulas are very good thing to represent molecule on paper, but they do not give us any idea about the 3D structure of the molecule. And you know, 3D structure is very important in order to study the reactivity of the molecule, because without 3D structure we do not know how the bonds are being oriented in 3D space. And not only the 3D structure, we also have to know that how these bonds can rotate, and we can have intermediate structure for a particular alkane, and they can be stable or they can be unstable. So, now we are going to discuss conformational analysis of alkanes. Now, what is conformational analysis? We have studied isomerism in our previous lecture. Now, conformational analysis means different spatial arrangement of atoms in molecules which give them different intermediate forms when carbon-carbon bond is rotated. So, basically conformational analysis is the arrangement we are getting when we are rotating carbon-carbon bond, and the intermediate structure we are getting are called conformers, which are interconvertible into each other and are non-separable. Sometimes we use term conformers, or we can also use term rotamers, or we can also use term conformational isomers. They all are representing the intermediate forms which are obtained when we are rotating something, because in our daily life when we are rotating something, then that structure is getting distorted. So, similar case is observed in case of our chemical structure. So, now let us discuss the conformational isomers of ethane. Ethane consists of two carbons. So, this is the structure of ethane: C, H, 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 then again we have this structure. So, two carbons. What we have? we have 2 carbons and we can rotate this carbon. Now, what is the phenomena behind this? That we need to fix one carbon and we need to rotate other one. So, when we are rotating at a certain angle, we are getting different intermediate forms. Now, there are 2 conventions through which we can represent conformational isomers. First one like this, I have carbon, we have 3 bonds, and what are we observing? We are observing, consider this hand as back carbon, this hand as front carbon, and at this point they are just eclipsing each other. That means the CH bond of back carbon are eclipsed on CH bond of front carbon. So, this state is called eclipsed conformation or eclipsed state of ethane molecule. Now, if I try to rotate it at an angle of 60 degree, I have carbon, back one is fixed and front one is rotated. So, this was the earlier condition, rotating the front one by an angle of 60 degree, I am getting this conformation. So, this is this, and this state of molecule is called staggered conformation. Staggered means they are not eclipsing each other, they are opposite to each other. Now, again if you try to rotate this, see, if I am rotating this, then I will get back to the eclipsed state. That means for ethane we are getting 2 intermediate forms, eclipsed and staggered. But this representation is kind of difficult representation. So, therefore, Newman gave a new convention method to indicate conformational isomers. So, now according to Newman's projection, I can represent these 2 states, back carbon with a circle and 3 bonds, and front carbon by simply joining 3 lines. So, according to Newman projection, this is the eclipse state for ethane molecule, rotating 60 degree, keeping the back carbon at the same position and rotating the front one by 60 degree, I will get the staggered conformation. So, this is the angle, this is called dihedral angle. In this case it is 0 degree and in this case it is 60 degree. So, we have 2 conformation according to Newman's projection, eclipsed and staggered. Now, in eclipse you observe that the 2 carbon CH bonds are overlapping with each other. That means whenever you are forcing something to come closer or to occupy a common space, then they observe certain kind of strain in the molecule. So, strain means that molecule is not in its optimal form or not in its stable form. So, now we need to understand what happens when there is strain in the molecule. In this case, when there is strain, then this is having comparatively higher energy as compared to staggered one, which indicates that higher energy ones are less stable and lower energy ones are more stable. So, therefore, eclipse conformation is 3 kilocalories more in energy than staggered one, and hence this is more stable. This is more stable and this is less stable. Why? Because it is having 3 kilocalories of energy more as compared to staggered conformation. And why this is so? This is due to the presence of strain. Now, before moving on to higher alkanes, you need to understand what is strain. Strain refer to anything which changes the stable form of the molecule. See, in daily life we see that in our pens we have a spring. When we press the spring, this is called compressed spring, we are applying pressure on the spring. That means this spring is under strain. But when you will release that pressure, then it will move apart. So, molecules which are having strain, it can be compressed strain or permanent strain or any kind of strain. Any molecule which is in strain is more reactive than which is not in strain. So, therefore, this is more reactive than this. So, we need to understand that in conformational analysis, there are 3 types of strain. So, now I am going to discuss 3 types of strain observed in case of alkanes. Basically, strains are of 3 types. First one is our steric strain. Steric strain, that means destabilization due to repulsion in the electron cloud, or in simple words I can say that the 2 groups are trying to occupy the common space. We observe steric strain. Second type of strain is torsional strain, is destabilization in the molecule due to the repulsion in its electron pair, or in simple words I can say when there is eclipsing of groups like we have seen in the case of ethane. So, eclipsing causes torsional strain. Whenever there is eclipsing, there will be torsional strain. And third kind of strain is angle strain, which is sometimes called as Bayer strain when we will study cycloalkanes. Angle strain, that means if there is distortion from the normal bond angle, or I can say normal dihedral angle, then we observe or the molecule experiences angle strain, and this is especially in case of cycloalkanes, which we are going to discuss later. So, these 3 types of strain causes instability in the molecule or in the structure. Now, we are going to observe these strain in the conformation of butane. Conformation of butane. Butane means it is having 4 carbons. That means 3 carbons are bonded to each other. If I number them 1, 2, 3 and 4, we can observe that if we rotate around C2 and C3, then we will get a symmetrical conformation. So, we will start with rotating C2 and C3 and we will get different conformations. So, now starting with the most stable conformation of butane. Now, we are going to start with the most stable conformation of butane. As I already told you that the molecule in which the strain is minimum, that will be most stable. So, this structure of butane is having CH3 and CH3 at a maximum angle, or I can say they are 180 degree apart. That means minimum strain and maximum stability. So, this number 1, this is the most stable conformation of butane and it is called anti. Okay. Now, what we do in conformation? We fix one carbon and we rotate the other one and the dihedral angle is 60 degree. So, now rotating it by 60 degree, what I will get? I will get, keeping the back fixed, so front carbon is now in the eclipsed position with the back carbon. CH3 is eclipsed with CH bond. Here the CH3 of back carbon is eclipsed with the CH bond of the front carbon. So, I will number it 2 and it is called eclipsed conformation of butane. Now, again what we will do? We will again rotate it by 60 degree and what we will get? Back carbon in its original position and front carbon with CH3, H and H. Now, in this case the 2 CH3 are at 60 degree apart. or I can say the dihedral angle between the two CH3 is 60 degree. So, this conformation is called gouge conformation. Gouge staggered, or I can, to be very precise, and I number it 3. So, up till now I started with the most stable conformation, rotated 60 degree, I get eclipse conformation, then again rotating 60 degree, I got gouge staggered conformation. Now, moving on further, you know, total rotation is 360 degree and each time we are rotating it by 60 degree. So, now rotating it with 60 degree, we will get back carbon in the same position and front carbon eclipsed. But here in this case, you observe that the two bulky groups are eclipsing with each other. That means the maximum strain is observed in this case. Why? Because this will be experiencing, this structure will be experiencing steric strain as well as the torsional strain. So, I number it 4 and it is called eclipsed conformation of butane. Now, again we have 4 structures up till now, then again rotating it by 60 degree, I get back to something like this. Fifth, and you see third one and fifth one, third and fifth, they are somewhat the same. In this case CH3 was on the left hand side, in this case CH3 is in right hand side. So, therefore, fifth conformation is also called gouge staggered conformation. Further rotating it by 60 degree, keeping the back carbon fixed and eclipsing of this group. So, this is somewhat similar to second structure. So, this is our sixth structure which is called eclipsed structure, and again rotating by 60 degree, I will get back to the structure with which we started. So, total rotation we have done is 360 degree, and in this rotation I have obtained 6 intermediate structure by simply keeping the back carbon fixed and front carbon rotating. Now, studying these structure, you can see that second and sixth and fourth also, they are eclipsed, but fourth one is having greater energy due to the repulsion of two bulky groups and experiencing steric as well as torsional strain. So, if I categorize this structure as the most stable structure, then this structure is the most unstable structure. Why? Because this structure is experiencing two types of strain. First one is the steric strain and second one is the torsional strain. However, the other eclipse structure are just experiencing torsional strain due to the two CH bonds and CH3 bonds occupying the common space. So, these are basically eclipse structure, but comparative to this they are more stable. So, now if I arrange them in the order of decreasing stability, I can say NT is most stable, then I can have structure number 3 and number 5, and then I can have 2 and 6, and then I will have fourth one. So, this is the stability order, most stable one this, most unstable one this. Now, if we study this in terms of energy profile diagram, So you will observe that this is lying at the lowest peak of the curve and this is lying at the highest peak of the curve. So looking at the energy profile of each conformer, I have NT which is lying at the lowest energy peak, I have staggered which is having around 3.8 kilojoules of energy, I have two eclipse structures which are having around 15 kilojoules of energy, and the most unstable structure which is eclipsing of two CH3 groups. Having 21 kilojoules of energy. This can be clearly understood by plotting the graph between energy and dihedral angle between the two CH3 groups. So this is the conformation of butane. Molecule with carbon-carbon single bond observe this type of conformational structures, but problem is that these conformations are converting into each other at a very fast pace and they cannot be separated, but they give us the idea about the stability of that particular compound. So today we discussed about the conformational analysis of butane and ethane. In the next lecture we are going to discuss conformation of cycloalkane. I hope you all have clear understanding about today's topic. Till then, keep watching. Thank you.